Welcome to the inaugural video in the series Deep Dives, Learning Things You Thought You Knew, where we start from elementary places and investigate how deep the mathematical rabbit hole goes. Full disclaimer, from the perspective of a professional mathematician, this is actually a very shallow dive. Check the video description for further references on some of the topics presented. In this video we'll discuss numbers. What are they, and what types of numbers are there? First things first. Let's discuss what this video is about and what it isn't about. If you've been paying attention so far, you know we want to discuss numbers, but this isn't a video about numerals or the different symbols we can use to write numbers. We are going to discuss how one number system can be developed into another number system for some purpose, but we're not going to learn the history of these developments. Honestly, I don't know the history. We definitely want to pay a little attention to some definitions, though not in a very technical way, but we won't be covering enumeration or ways to count things. There's a whole bunch of mathematics related to techniques of enumeration, and we're not doing that today. Along with this focus on definitions over techniques, we are going to be talking about the pure math theory of these number systems, but I'm not concerned with any practical applications of these things. I'm just kidding. We'll definitely mention applications. As long as we're going to discuss definitions in some technical detail, when we ask what is a number, we can make our first distinction. Sometimes when people talk about numbers, they're talking about cardinal numbers, and sometimes they're talking about ordinal numbers. What's the difference? Well, the worst thing I could do right now is to quote a dictionary definition. But I'm going to do it anyway because, as part of my research for this video, I found this definition, emphasis here is mine, that manages to squish both cardinal and ordinal numbers into a single definition. Most dictionaries I found had the two ideas separated, but not this one. The basic distinction is that cardinal numbers are about counting things, or how many things are in a collection. We call this notion cardinality in set theory. Whereas ordinal numbers aren't just ordinary, but ordered, or orderedly ordinary. They're about order. So let's talk about cardinal numbers, the counting numbers. Are there any cardinal numbers that you may have never seen before? I like birds. Let's talk about 6, the quantity of sixness as a cardinality. Here are 6 stars, and here are 6 happy faces. Happy faces aren't stars, so these are not the same thing, but we still use the word 6 to talk about how many there are of each. Somehow, 6 is an abstraction about quantity that isn't tied to a specific object. Those are the cardinal numbers. More birds. Okay. Now, there are certainly numbers that aren't about counting how many objects we have. 1/2 is a number, I imagine. That's not a controversial statement. But it can't refer to how many. It can perhaps refer to how much, but that's different. There are also things that aren't always thought of as numbers, but which can describe how many. As much as I viciously mock my analysis students for treating infinity like a number, we can certainly conceptualize infinity as a quantity. In fact, there are different sizes of infinity, and cardinalities that aren't finite we call transfinite. Why not just infinite? I don't know, ask a set theorist. I don't associate with those people. So let's talk about transfinite cardinals, like the pure Loxia. Here we have all if not, all if 1, etc. Or all if 0. I said all if not, like a notch for not like it's not a not. Both not and 0 are used when talking about that subscript. I'm not sure how I picked up the not convention. I'm just naughty, I guess. Anyway, all if not is the quantity of counting numbers, 1, 2, 3, etc. How many of those are there, all if not? All if 1, all if 2, and so forth refer to larger and larger cardinalities. Yes, there are sizes of infinity larger than other infinities, but that's not the topic for this video. It's totally possible to define what it means to add or multiply these infinite cardinalities. We won't do it, but it's been done. Well, if there are strange new cardinals, are there bizarre and unexpected ordinal numbers, positions we've never conceived of? Well, they would have to refer to positions beyond every finite position. What comes after first, second, third, and all the rest? Well, yes, these things have been thought about. I hate to disappoint my viewers, but we're not using these videos to develop ideas heretofore unknown to mathematics. Just like we used a new symbol to represent cardinalities bigger than all finite numbers, we use omega to represent the first ordinal number larger than every finite number. And then there are systems of arithmetic on these numbers as well, and again, we're not going into the details, but it's been done. So now, a quick overview of the standard number systems most of us are probably already somewhat familiar with. We may have all seen this before, where one collection can be viewed as a subset of the next. We start with the natural numbers, our basic counting numbers. Cardinals, ordinals doesn't really matter to us anymore. But there are no negative numbers yet. So we add in negative whole numbers and we get the integers. Then we add in so-called fractions and get the rational numbers. I say so-called fractions because lay people often conflate rational numbers and any non-integer when they use the term fraction. Well, then there's the real numbers, commonly visualized as the number line, and then containing all of them, there are the complex numbers. End of story. So let's start with the natural numbers, the counting numbers. There's one question to address at the start. Do we begin counting numbers at 0 or at 1? In other words, do we start 1, 2, 3, and so forth, or do we include 0 at the beginning? There's no universal convention, actually. It may surprise you to know that this isn't totally settled. You may have thought one way was standard, and are actually surprised now to learn that other people disagree with whatever you thought the obvious choice was. But I'm going to settle the issue once and for all. In the matter of, is 0 a natural number? The answer, from now on, for everybody is yes. Right, with that settled forever, let's talk about arithmetic. You know, math, or maths, or maths, mathematics. But seriously, we'll talk about operations on numbers. You take two numbers, do some nonsense on them, and you get out one new number. Anytime we discuss an operation, we'll ask several questions. First up, what happens if I try to act on the same two numbers but in the opposite order? Does that matter? If not, the operation is called commutative. Next, what happens if I try to do the same operation in succession? If the order in which I perform this operation twice doesn't matter, then the operation is called associative. If we've already got other operations floating around, we can investigate how our new operation interacts with the old ones. Maybe the operation has a special buddy number that lets you ignore the operation. Some special number where the operation sees that number and says, never mind, just do nothing. Those are called identity elements. And if identity elements exist, can you transform any number you want into the identity element? That's called inverting your operation through the use of inverse elements. Having said all that, we're going to start with just the number 0. It's the only number. 0 is the loneliest number. And our first operation is called succession. Thinking about ordinal numbers, the successor of a number is just the next number. While for cardinals, taking the successor of a cardinality amounts to adding one more thing to the size of the collection. There are different ways to talk about this, but something called Peano axioms are a user-friendly way of doing it. For example, we declare that 0 is a number. Also, if two numbers are different, then their successor is different, and nothing has 0 as its successor. There are other Peano axioms, but just from these, we start to do some stuff. 0 has to have a successor, but it can't be 0 because 0 is never the successor of anything. So call this new number 1. Then 1 has to have a successor, and it can't be 0 because 0 is never the successor. And it also can't be 1 because 1 is already the successor of 0. Since different numbers have different successors, 1 can't also be the successor of 1. So call this new number 2. And we keep going. 3 is the successor of 2, 4 the successor of 3, etc. The other axioms that we aren't mentioning help keep weird things from happening, but you get the point. The successor operation is going to define natural numbers for us. There weren't really any properties to discuss for the successor operation because it only acts on one number. Let's talk about a new crazy operation, addition. which can be thought of as iterating succession many times. Well, if you add two numbers, how does that compare to adding them in the other order? As we all know, it doesn't matter. The two sums are identical. In formal functional notation, the sum of a and b is the same as the sum of b and a. What happens if I take two sums in a row? Again, we all know from elementary school that the order doesn't matter. We're not going to keep using this formal functional language, but here it is. The sum of a and the sum of b and c is equal to the sum of a and b and c. So addition is commutative. That's cool. What happens if I take a sum and then a successor, or a successor and then a sum? Formally, there's a Peano axiom about it. Here it is. We're not focusing on rigorous proofs through Peano axioms here, but it turns out that the successor function is the same as adding 1, which you probably already guessed. So on the left, the successor of the sum of a and b. On the right, the sum of a and the successor of b. They're equal, no surprises. So what's this stuff about identity elements? Is there something that sums can effectively ignore? Yes, 0 is a number that never affects sums. Adding 0 to any number a does not change the value of a. So then we can ask if there are inverse elements. Is there something you can add to a in order to get out the special number 0? In general, there are not such numbers within the natural numbers. I can't add anything to 2 and get out 0 because the only numbers I have at my disposal are 0, 1, 2, 3, and so on. So while we have the operation of summation, it can't be undone because there are no inverses for addition. So we just declare that they exist. If only other problems in life could be solved by fiat. Whatever a is, we declare that it has an additive inverse, and we use the symbol minus a to represent this new number. And now we have all the integers, natural numbers and negatives. The natural number 0 is actually its own inverse for addition. The number to add to 0 to get out 0 is already 0. In other words, negative 0, the additive inverse of 0, is just 0. You can show that addition is still commutative and associative even with these negative integers included. That's good. We didn't break anything. Now that we're in a new number system that has additive inverses, we can define a new operation called multiplication, which is just iterated addition. This operation is commutative and associative. We all know this already. The point is that it's possible to prove these things even if we're not going to take the time to do so. With two functions on the operating table, we can see how they play together. Take a sum and then a product, distribute. We also have this multiplicative identity. Multiplying by 1 does not change the value of something. If we know that 1 is a multiplicative identity, can we find multiplicative inverses? In other words, can we find something to multiply against a and get out 1? Since our universe is just whole numbers, integers, it's not usually possible to do this. So we do the same cheap trick that we already did. Just declare them to exist. Whatever integer a you have, just write 1 over a to represent this multiplicative inverse. That is, 1 over a is just a number that when I multiply it by a, we get out 1. Just like 0 was its own additive inverse, 1 and negative 1 are already their own multiplicative inverses. Here we see that since the number to multiply 1 by and get out 1 is 1, 1 over 1 is 1. And since minus 1 times itself is also 1, 1 over minus 1 is the same as minus 1. These statements are true, mind you, because the very definition of a multiplicative inverse of a number is the thing you multiply by to get out 1. But for other integers, we need new numbers. For example, there is no integer which when multiplied by 3 produces 1. So we invent the new number, 1 over 3, to have this property. That's how we are defining this notation. These new numbers are just defined by this multiplicative inverse property. Very quickly though, why is there no such thing as 1 over 0? And why can't we just define it however we want to, like we have with prior obstructions? The short answer is that a combination of the distributive property and the provable fact that the only additive identity is 0 prohibit 1 over 0 from having any value at all. Take any integer x. Since 0 is the additive identity, x plus 0 equals x. Multiply both sides by b. Our proposed number, which is to be the multiplicative inverse of 0. Use the distributive property on the left, but now we see that b times 0 was added to b times x on the left, but just produced b times x on the right. The only number that doesn't affect sums is 0. So b times 0 must be 0. So we can't let b be a number which is the multiplicative inverse of 0, because any number b times 0 must be 0, not 1. Our rules of arithmetic force our hand. 0 cannot have a multiplicative inverse. If we iterate multiplication, we get exponentiation. But things get a bit different here. Exponentiation as an operator on two arguments isn't commutative. A to the b isn't always the same as b to the a. And it's not even associative. Exponentiating an exponential, order matters. Interaction with addition and multiplication can be determined, but that's all familiar to us. Without commutativity, the question of finding identities has to be split into right-sided and left-sided problems. There is a right identity. Anything to the first power is itself. But there's no left identity, something which to the power a will always be a. We have a universal inverse element for that right identity of 1, which is quite different than additive inverses and multiplicative inverses changing for each element. Except 0 is 0 to any power equal to 1. The short answer is not exactly. If 0 to the 0 is some number b, then since any non-zero b to the 0 power is 1, either b is 1 or b is 0. These are the only choices consistent with our various rules of arithmetic for exponentials. Now, on the other hand, anything to the 0 power is 1 suggests that we should set 0 to the 0 equal to 1. On the other hand, 0 to any other power is 0, so maybe 0 to the 0 should be 0. Honestly, depending on the situation, either one could be appropriate, and sometimes you'll see either choice being made. But it really depends on the situation. Setting 0 to the 0 equal to 1 is more common, but most common is to just say it doesn't have a consistent value at all. Either way, if it matters in what you're doing, you should tell your audience what you're doing. Well, we're pretty deep into this video, and the rational numbers are pretty cool, so let's just call it a day. We've got whole numbers, and we divide them into pieces. That's something we can all wrap our heads around, so thanks for tuning in. It's been fun. I'll see you in the next one. So let's actually talk about geometry. If a square has side length x, it has area x squared. So here's a square with side length 1 and area 1, and here's a square of side length 2 and area 4. So can we pick an x to get an area of 2? Some side length in between 1 and 2 should work, right? But no, there is no rational number p over q so that the square is 2. Here's a very short proof. If p squared equals 2q squared, then p squared is even. It's 2q squared. But if p is odd, p squared is odd. Therefore, p must be even. In which case, p squared is divisible by 4. So since p squared equals 2q squared, and p squared is divisible by 4, 2q squared is divisible by 4. Therefore, q squared is divisible by 2, which means q can't be odd. So both p and q must be even, in which case we could simplify our initial choice of p over q by canceling that shared factor of 2, and try again. But then we've just argued that our new p and q must have a 2 that can be canceled out, etc., etc., etc. We found an infinite descent. We can cancel 2's forever, even though we started with finite numbers. So we've maybe found a compelling case for an intuitive understanding of some numbers as measurements that aren't rational. If we have a positive rational number whose square is less than 2, we can find a larger rational number whose square is also less than 2. And if we have a positive rational number whose square is larger than 2, there is a smaller rational number whose square is also less than 2. So here's the number line. Some rationals have squares less than 2, but there is no largest such number. Some rationals have squares larger than 2, but there is no smallest such number. Oh no, we've had a math disaster. The rational numbers are chock full of these holes, missing values that go against how we think of a continuous line of values. In fact, the cardinal number for the quantity of missing values is larger than the cardinal number for the quantity of rational numbers themselves. If we only have the rational numbers, there are more holes than there are points, which is weird, but true. I mean, any one of those holes must have rational numbers on either side, so how can there be more holes than points? How? But it's just true. So the real numbers have got some weirdness that the rationals didn't have. Do we really need irrational numbers? This business of filling in the holes, of which there are very, very many, is really quite important. We don't lose any of the arithmetic we could do with the rationals, but now we gain a completeness property. This completeness property, that a set which is bounded above has a smallest upper bound, allows us to do some useful stuff. In addition to the orderedness and inverse elements existing, it really defines what the real numbers are. These things all together allow us to develop calculus, which is pretty useful stuff. So we can develop this broad definition of what a number field is, which is an abstract algebra flavored statement. We have to be closed under two operations, and they're both commutative and associative. Each operation has an identity that we usually denote with the standard symbols, and inverse elements exist for these operations at least as much as they can. Throw in the distributive property and you've got yourself a number field, baby. So have we seen these things before? The natural numbers don't have additive inverses, so they're not a field. No multiplicative inverses in the integers, so they don't form a number field either. But rational numbers have all these properties. They're a field. Real numbers also have all these properties, so also a field. But we can make more and more number fields. We just want to be sure that we have sets with arithmetic that behaves like we think it should. But if we want polynomials to be solvable, i.e. have roots, we have a problem. In the real numbers, it's pretty easy to make polynomials without roots. Here's one. No real number solves this equation. But we can invent a new number because we have that power. We call it I. This new number just happens to solve that equation because we say so. If we add this into the real numbers and force it to still be a field, so there's an additive inverse and a multiplicative inverse for I, for example, then we get the complex numbers. And what's pretty neat is that all polynomials now have roots, just with that one addition. So we've reached the end of the game for polynomials. But hey, they're called imaginary, so they don't exist, right? Why not? Because you can't square something and get out a negative number? Who says? Until we invented irrational numbers, this equation had no solutions. And until we invented rational numbers, this equation had no solutions. And until we invented negative numbers, this equation had no solutions. The complex numbers are just another step in this line of thinking. They exist in just the same way that any of our other numbers exist. I mean, as much as any number can be said to exist, so do complex numbers. And they're actually very useful, like really, really useful. In actual physical scenarios, complex numbers are the unit of impedance in electrical circuits. You measure meters in real numbers and no one objects. Well, impedance is measured in the complex numbers. That's how impedance works. Multiplication by complex numbers covers rescaling. Like multiplication a number by 2 makes it twice as big, but complex numbers also have a two-dimensional rotation to them. Multiplying by -1 reverses something, right? Like a 180-degree rotation. Well, multiplying something by I rotates it by 90 degrees. Do that twice to get 180 degrees. In other words, reverse it. Multiplying by I twice is the same as multiplying by -1. I squared is -1. There. Deal with it. A mathematician never saw an idea without the strong urge to abstractify it into a terrible state, so we can keep going with these notions. Yeah, we get a lot of onions. There's quaternions. In addition to I squared being -1, we introduce j and k with the following properties. They also square to -1. But the triple product ijk is also -1. With these rules, one can show that multiplication is not actually commutative, so we're not technically a field anymore, but we are something called a division algebra. Now we can model 4-dimensional rotations, and therefore also 3-dimensional rotations. These are used in some situations to make a simpler representation of 3-dimensional modeling. Then there's octonions. We have 8 special symbols with various rules for their products. Well, 7 special symbols and then 1. The rules involved make our operations not even associative, not a field. Sometimes physicists want to sound like they know more than mathematicians and they'll trot these things out, but that's their only use. You can keep going, getting the Sidonians. Here you have 16 special unit elements. They're only used to show off. I do think it sounds like a very plausible name for like an alien race or a fantasy nation, the Sidonians. I'm going to use that sometime. But there are interesting number fields that we can build. If we want addition and multiplication to behave like we're used to, and for inverses to exist, we want all the rational numbers. So until the very end, we'll keep the rational numbers as our starting point and briefly run through a bunch of other number fields that get thrown around. First up, what are called constructible numbers. Okay, what does that mean? Think back to planar geometry, making figures using only a compass, which can duplicate distances that already exist, and straight edges, which can draw a line connecting any 2 points that already exist. Just from these techniques, we can make irrational lengths. Start off by jabbing the pointy bit of your compass anywhere. You've got a point. That was fun, so do it again. Now we have 2 points. Connect them with a line. Mark off the distance between them with your compass and draw a circle of that radius centered at one of the points. We won't go over all the steps, but it's possible to use a compass and straightedge to make a line perpendicular to an existing line through a point on that line, so we've done that. Now, draw another circle centered at the other point you started with, still with the same radius. Mark off the point of intersection between that perpendicular line and the second circle. We'll presume our initial 2 points were distance 1 apart. It was the only distance that existed when we started off. Then these points are also distance 1 apart, since we're marking off the distance to the center of the same circle they're on. We can use our straight edge to make a segment connecting these 2 points. By the Pythagorean theorem, then, this segment is of length square root 2, which we've already seen isn't a rational number. Okay. Enough pictures, back to the exciting part, text. It turns out that all the lengths you can make in this way form a field. Is that interesting? At the very least, since there are real numbers that actually aren't constructible, it shows that the number line consists of a lot of values that are somehow physically inaccessible. That's not so easy to prove, but it's true. Are there practical applications for these constructible numbers? Well, they were developed to address some very, very long-standing problems that had vexed geometers since geometers were getting vexed. Like, can you make a cube of volume 2? No. Can you always divide an angle into 3 equal pieces? No. Can you construct a regular 7-sided figure? No, not with a compass and straightedge at least. Next up, the field of algebraic numbers. So, what are those? Starting from the rational numbers, presume that all polynomials with integer coefficients have roots, and make a field with those numbers. You can decide to add all of those numbers or just some of them. That sounds convoluted. If you add all those numbers, you get a field that allows you to solve all polynomials, but still doesn't include all real numbers. If you add just some of the roots of certain polynomials. You can build some intermediate fields, bigger than the rationals, but not all these so-called algebraic numbers are included. As your eyes glaze over and you beg for the sweet release of cocomelon, however, these intermediate number fields were used to study the question of which polynomials could be solved with explicit formulas like the quadratic formula. It turns out that for polynomials of degree 5 or larger, there is no corresponding formula, and there can never be. Next up, the computable numbers. They're not quite the same as constructible numbers. Loosely put, these are quantities that a computer program could theoretically approximate as close as you want in some terminating algorithm. If you're with me so far, you may think that's interesting. We still get a situation where most real numbers are not included yet. So not only are most real numbers irrational, but most real numbers can never even be approximated by any computer program ever. I mean, the result is interesting enough, I think, but there's also a whole school of mathematical philosophy that says we should only be concerned with numbers that can actually be reasonably approached, not just abstract nonsense that we can think of. I'm not a constructivist, but I hear that they exist somewhere, abstractly. Now we're getting weird. Number fields with infinitesimal numbers are a little bit different. There is no positive number smaller than every other positive number, because you could just multiply it by 1/2 and get smaller. But what if there was a number which was positive, but at the very least smaller than every positive real number? Let's call it epsilon. That can't be a real number, but we're making new number fields, so whatever. Now, what you do is you see how arithmetic is affected by the inclusion of this number and the presumption that you're still a field, closed under operations, inverses exist, etc. Now, it's common for students just starting real analysis to say things like, suppose you take the smallest positive real number. That doesn't exist, so those students are wrong before they even start. But what if you just change the rules so that there are such infinitesimally small positive numbers that aren't real? Well, something so small can't possibly be interesting, so no. Actually, historically, mathematicians used infinitesimals for informal arguments in calculus to get an idea of how things were working, even if not in a totally rigorous manner. So, if we have this new number field, can we actually use it for something? In the end, it is possible to spend some time formally justifying that these number fields behave nicely enough, and then using them, you can take a radically elementary approach to calculus. Now we get to a point where the only viewers left watching are either in totally new territory or other mathematicians leaving nasty comments about all the mistakes I've made so far. So what are these things called p-adics? p-adics. It's complicated, but imagine you're taking a decimal expansion for numbers, only you're not working in base 10, but a prime base. Also, you're not building infinitely long chains of digits to the right of the decimal point, but to the left of the decimal point. Well, that's a loaded question. Okay, they actually are. They can be constructed as a completion of rational numbers under a different way of measuring distance. That's fun, I think. Are they useful in any practical way? Yes, so long as you accept used to prove stuff in higher mathematics as a valid application. Supposedly, some of these number theoretic results have seen some use in physics recently, though I don't know anything about that because I'm not a physicist. I don't know any physicists, and they won't return my calls. I think they don't recognize the sound of a ringing phone because nobody ever calls them because they're physicists. Silly mathematician, all fields are finite since they're confined to the surface of the earth, ipso calypso. But seriously, what's a finite field? Now, the definition of a field doesn't actually require infinitely many elements. Closed under operations, inverses existing. Distributive property, that's all. So what if we just declare, say, that 5 and 0 are the same number? Then we don't need fractions to have multiplicative inverses. If 5 equals 0, then 6 equals 1. Therefore, 2 times 3 is equal to 1. So 2 and 3 are multiplicative inverses to one another. Further work will show that just the numbers 0, 1, 2, 3, and 4 can form a field when you make the presumption that 5 equals 0. Also called modular arithmetic or clock arithmetic, because 2 hours after 11 is 1, not 13 o'clock, and put your hands down, 24-hour clock enthusiasts, you get the point. So are these things interesting beyond simple examples like clocks? A whole lot of interesting, actually. These finite fields can be studied and classified and poked and prodded through abstract algebra, and we want to do that because they're actually very useful. Modern encryption techniques rely on mathematics of finite fields. You couldn't order your fake vintage concert tour t-shirts using a credit card online without finite fields, for example. Okay, that's enough for now. Hopefully you've learned something about numbers. If you want more details about some of the topics we've discussed, check the video description. If you want more information and don't see a reference in the description, drop a comment to ask about it. Bye, be good.